In Chapter 9, Question 18, they're asking if several solutions are isotonic, hypotonic, or hypertonic. And to get a handle on what's happening in this problem, we want to think about a big principle, which is that water follows a solute. So if you have more solute, either salt or sugar, in one place than in another, water is going to go to the place that has that more salt or sugar. Now, inside of a red blood cell, there is a 0.9% mass volume of table salt, NaCl, and 5% sugar mass volume. And so you can put a red blood cell into 3 different types of solutions. In one solution, there would be more than that amount. There's either more salt or more sugar in the solution. And if there's more outside of the cell, water is going to go where the solute is. It's going to follow it. So if there's more outside, then the water is going to go out of the cell. And when it does that, it wrinkles or shrivels up like you see here on the right. And so if you have more solute in the solution, the word Greek prefix for more would be hyper. The word for solute is tonic, and that's to describe the solution outside of the cell. So that solution outside of the cell has more solute, so it's hypertonic. And the cell shrivels up. So the fancy way of saying shriveling is crenates. So that's shrivels or wrinkles up. That's the first scenario. A second scenario is if you have equal amounts of salt and sugar inside and outside the cell. And if it's equal amounts of salt and sugar, the water doesn't prefer to be in one or the other, so it doesn't change. There's no change. Now, the word you have equal amounts inside and outside the cell. The Greek prefix for equal is iso, and then again we're talking about the amount of solute, so tonic. So it's an isotonic, and this is describing the solution outside of the cell, so an isotonic solution. And when that happens, the cell does not change, so there's no change. Okay, last case is if you have less salt or sugar outside of the cell than inside. If there's more salt inside the cell, then the water follows that solute. It goes into the cell, and the cell swells up until it bursts, like you can see here on the right. Okay, when it bursts, it's a blood cell bursting. The Greek prefix for blood is hemo, and for breaking apart or bursting is lysis. So hemolysis occurs. The cell bursts and spills its guts all over the solution. And the name of the solution that had less solute, the Greek prefix for less is hypo. For example, if you're hypothermic or suffering from hypothermia, you have less of a heat than you would normally have. So hypo, and again, we're talking about the amount of solute, so tonic. So it's a hypotonic solution outside of the cell. The solution outside of the cell has less solute, so it's hypotonic. So these are our 3 cases that result from water following solute. So armed with this information, we can approach these questions. The first one asks, what would happen? Is this solution here isotonic, hypotonic, or hypertonic? Now, if you have distilled water, what you have is only water. It's just pure water. If you have pure water, how much salt is there? There is 0 salt because it's pure water. How much glucose is there? 0 glucose because it is pure water, which has nothing else in it. Otherwise, it wouldn't be pure. Okay. So now we want to look at these values, 0 on the outside, 0.9 and 5 on the inside. Which one's bigger? The inside, so water follows that solute, goes into the cell, and ultimately the cell swells up and bursts, like we saw in case 3. So that is what happens here, and we can see that because you have less solute outside, it's a hypotonic solution, and you would get hemolysis. They're just asking, is it isotonic, hypotonic, or hypertonic? So for this one, you'd say hypotonic. Okay, how about B? For B, they say you have a 1% glucose solution, mass volume. Okay, so we're going to compare that amount of glucose to the amount of glucose inside the cell. 5% inside, 1% outside, there's more inside the cell, so water rushes into the cell. The cell swells up until it bursts, and again, you have that third case, a hypotonic solution where you get hemolysis. So again here, we have hemolysis occurring, and it's happening because the red blood cell is in a hypotonic solution. For C, they tell us that we have 0.9% sodium chloride mass volume in the solution, so outside of the cell. So we're going to compare that 0.9% outside with the 0.9% inside. Well, those are equal, so that's the second case we saw, where it's the same outside and inside, so there's no change. And the term for the solution would be an isotonic solution. So the solution is isotonic, iso equal, tonic solute, and as outside the cell is inside the cell, so there'd be no change with that one. For D, they say that you have 15% mass volume glucose, and so we're going to compare that 15% outside of the cell with the 5% inside the cell. 15% is bigger, and so water follows the solute. It goes where there is more. So it's going to go out of the cell, and the cell will shrivel up because it's losing all that water. This would be the first case that we saw. The water rushes out and shrivels up or crenates, and it happens because it is in a hypertonic solution, a solution that has more solute in it than the red blood cell has. So that would be how you'd answer question 18. Now question 19 is asking pretty much the same thing, except instead of asking you to describe the solution as hypotonic, hypertonic, or isotonic, they're asking you what the response of the red blood cell is: crenation, hemolysis, or no change. But the way you analyze it is the same. If you have 1% glucose in the solution and 1% mass volume, we're going to compare that 1% outside the cell with the 5% inside. So which is more? 5%. So the water follows the solute, goes where there's more. It rushes into the cell swells up and bursts. That was our third case here, where you had a hypotonic solution that caused hemolysis. So as the water rushes into the cell, it bursts open, and you get hemolysis. For B, they say you have a 2% sodium chloride solution. So 2% outside of the cell will have 2% mass volume sodium chloride. We're going to compare that 2% with the 0.9% inside the cell, which is bigger, the 2%, so water follows the solute, goes where there's more of it, rushes out of the cell shrivels up and crenates. That was the first scenario here. When water rushes out of a cell, it happens because it's in a hypertonic solution, and that cell crenates or shrivels up. For C, it says you have 5% glucose in the solution, so 5% mass volume glucose. So we're going to compare that amount of glucose outside the cell with the 5% inside the cell. Those are equal, and so this is an isotonic solution, and there would be no change. If the concentration is equal inside and outside of the cell, then water doesn't prefer to be anywhere. It doesn't have a higher concentration of solute to follow, so it just stays, and you get no change. For D, it says that you have a 0.1% mass volume solution of sodium chloride. So we have 0.1% mass volume for sodium chloride outside of the cell. We're going to compare that 0.1% with the 0.9% inside, which is bigger, 0.9%. So water follows the solute and goes where there is more. It goes toward the bigger number. And so it's going to rush into the cell until the cell swells and bursts open. And that was our third case here where you get hemolysis. So if that water rushes into the cell, then the cell swells until it bursts, and that is hemolysis. So that's how you can assess these different scenarios. You can imagine how important this would be to a nurse. You'll be injecting IV solutions into somebody's blood. You have to make sure that the solution is always 0.9% mass volume sodium chloride, 5% glucose, or all of their red blood cells will either shrivel up or burst open. In either case, the patient dies. They only survive if the solution you inject into them in the IV is isotonic.